So, okay, so recording has started. So I'm just, I have started the recordings. Sorry. So again, that I was explaining that about the atoms, that why particle physics, and after that we went to atoms, that matter. What when someone mentions matter, then atoms come in your mind, and there were different models of atoms, and different modernization and advancements have taken place. So, if I talk about atomic theory through the years, so then you must be knowing about different models. So, I'll be explaining you in a brief about various models. So, first is the solid sphere model, which was given by John Dalton. So, as you know, he considered that atoms were indivisible, indestructible, and also they combined in fixed ratios to form compounds. So this was the solid sphere model of by John Dalton. Later on, J.J. Thomson proposed another model, which is known as plum pudding model, which showed that he proposed that uh, elect, positive charge is just like a spherical, just like a sphere, and electrons are embedded in it. So, and next, the model which was given by Rutherford, which is known as nuclear model. So, which shows that atom consists of tiny, dense centered nucleus, and this was a big breakthrough in the like out of various models. And now, if I again come to Niels Bohr model, then uh, Niels Bohr, what he did, he just made the picture of Rutherford's model more clear, right? So he devised new terms called shells or energy levels, where electrons were there and they can jump to different shells, which we call electronic transitions, and they can either emit or absorb energies. So now finally we have come to a very important model which we use now. Now this is our model. So which is quantum mechanical model. So quantum mechanical model talks about the probability distribution, talks about orbitals, not orbits. So orbitals is mainly the area or region around nucleus where there is presence, like probability of like finding electron. So this model we use in chemistry also. You might have seen, you might have read. So now we have come to quantum mechanical model, and this is 100% valid now. So just like I have explained you in this slide, it's given that atomos, what is the meaning of atoms? Now the main things that we knew about three fundamental particles: electrons, protons, and neutrons. So, but scientists did various experiments. Like if I talk about uh, experiments that was carried in 1960s, then scientists found some particles that are beyond this proton neutrons, which are called quarks. So quarks are the smallest fundamental particle which we know, and nothing can be smaller than quarks. So we during yeah, so it's written here that experimentally confirmed via deep inelastic scattering. So through experiments, we can see quarks. Like now also we can see quarks uh, at LHC, which is the Large Hadron Colliders at CERN. You must be knowing about it, or we'll be discussing about it in the next session about different colliders. So you can get to know more about quarks. So before coming to the structure of proton and neutron, let's first understand that what quarks are. So quarks, as I told, it is the smallest fundamental unit, and also there are different things called flavor, color. It might remind you of some favorite dish, and or why is it called quark? There is another story. So we'll be looking at each and everything. So yes, quarks are the only fundamental particles, and we define and there are six types of quarks. Like mainly, if I go explain you the meaning that if I directly go to the types of quarks, then I think it will be fine. So there are six types of quarks. So first is up, then down. Everything is mentioned in this PDF. So it is up, down, charm, strange, top, and bottom. So, and also I'll be discussing the different properties of up, down, and charm, strange, and top, bottom quarks. But before that, we get to know that we should know that up and down quarks are found in nature. And that is why in protons and neutrons, just remember this point, that in protons and neutrons, we see up and down quarks. These are the valence quarks of proton and neutrons. So if we see the proton structure, then yeah, so you can see that it is made of two up quarks and one down quarks, and neutron is just the opposite, which is made of two down and one up quark. So why is it two up? So we can also explain this by the charge conservation. So we know that the up quark, as it is in this slide, yeah. So our quark has a charge 2 by 3 electron plus 2 by 3, and the down quark has the charge minus 1 by 3 electron, right? So if we apply charge conservation, then we say that 2 up quark in proton, which means 2 into 2 upon 3, which is 4 upon 3, and 1 down quark, which is minus 1 upon 3 electron. So the total charge becomes plus 1, right? Are you getting that the total charge becomes plus 1, since the charges are fractional here. And also neutron, y- I think it's your task to calculate that is it coming to be 0 for neutron. 2 down quark means what? Down quark has minus 1 upon 3 electron charge. Then again with charge conservation, it is coming to be 0. Now, again, there is one more thing, which is the color. Like you might be confused that why the color written it's white, but we are showing colorful quarks. So the more about color I'll explain you later, but mainly we talk about red, green, and blue colored quarks. And if we combine the colors of red, blue, and green, it becomes white, right? So that is why we can explain that why protons are colorless, or we usually write it white. So these things can be thought. And also, there are some of the important things written here, mentioned, which is the mass and neutron decay, and also the proton decay. So we'll talk about proton decay and neutron decay. So an important thing comes here, that a proton has three quarks, right? And the sum of the masses of the quarks is 9.4 MeV square, which is the energy unit, and the proton mass is too high. So the mass of quarks is less, but proton mass is too high. Why is that? So can we think about something that the sum of quark masses are less and proton mass is too high? So how does the proton's mass come from? So that's a very good question we can think. So for that, I think we need to understand something called gluons. Yeah, again, name of one more.
Anushka, your voice just stopped. I can't hear you. Can't hear you. No, we can't. Maybe just try reconnecting your headphones or something.
Uh, Hello, is it fine now?
Yeah, this is fine.
Okay, so sorry, there was very problem. There was a problem. So what was I explaining last? Like gluons, right?
Yeah, you just
So
mentioned gluons and then your voice.
okay. So yeah, so the main thing is that why did I mention gluons? What is the role of it? And right, so that's what I was talking about, the interactions of matter and like quark matter interactions. And we talk about some force carriers. So that's why I named the term gluon. So, and gluons can be imagined as suppose you are standing on a boat, okay, and your friend is standing on the ground somewhere, and your friend has a very heavy ball of or any object, very heavy object, and he or she throws that towards you. So, which is obvious that since you are on a boat, so you will move. So, if you will again throw that heavy ball, you will again move, right? So, this is what these kinds of interactions, which is also going in the micro world, right? So, these kinds of interactions are also going in the micro world, and that's why we need gluons, which keep the quarks together. These are the force carriers. Since quarks are moving at the speed of light, like compared to the speed of light at a very high speed, right? So that's why we need something to bind to, like to fix that, right? So that's why I was talking about gluons. So mainly, where does the proton's mass come from? So the force carrier, the energy transmission, all the energy transmission which is going through, these things add to the mass of proton. And of course, gluons, energy interactions play a very important role in giving mass to protons. And similar, it is the case for neutrons also. That why neutrons are also heavier compared to the quark masses, then we can explain with the same phenomenon. Okay, so now flavor and color that I'll be explaining. So similarly, here are some of the properties of up and down quarks, and always remember that these are more stable and these thus abundant, and that's why these are found in the protons and neutrons. So here it is the charge which is being written that up quark has charge plus 2 by 3 and down quark has minus, yeah. So, so these are the mass values which are written. So these points are important. You should keep in your mind that usually stable and can decay into down quark and positron and electron neutrino. And again, it can decay into up quark electron and an electron anti-neutrino. So yeah, the names are quite strange. That why is it named charm and strange? So that's what physicists do, right? They come up with some weird theory, they name something weird, and thus they make up. Especially it happens in quantum mechanics and particle physics. So yeah, so again, these are the properties, and also the heavy first of the quarks, which is the charm quark, and also it can decay into the strange or down quark. So these are some of the properties that you can read and keep in your mind, and I'll be explaining everything in the further slides if required. So yeah. So I know at this point, if you're not understanding what is Higgs coupling, I know you will not understand. We'll be explaining you everything. So that CP violation or something, I'll be explaining. Right. So here comes a very important thing, which is parity violation. It's very important to
There are a
understand.
couple of questions. Someone asked you to repeat a bit about gluons, and
Okay,
they're asking if we can separate the quarks and why electrons don't happen.
okay. See, the main thing is that we can think of a rubber band. So it's like that. That even if you separate the rubber bands, it's going to come up like this, and you require a huge amount of energy. And also, if you can separate, you can let the quark go, but again it will create some anti-quark, and these pairs just keeps on going on. So even if one quark separates, it can, like, you can knock off that quark, but still it will not be that stable. It cannot, quarks can never exist alone. Always remember, quarks can never exist alone, right? So, and that's why just see one concept called jets. So it is similar phenomenon. Why do we see jets? That if you knock off one quark, it can create anti-quark and like anti-particles, some of the, and it can, like, these particles can loop, and it can create jets. So it's not like that gluons can be separated from the quarks. So I hope you have understood. Yeah, so don't worry, I'll be explaining about gluons and all these kinds of particles again. If I like, I'll be reaching the standard model and I'll be explaining about it again. Don't worry. So this is just for you to understand that what holds the quark together. These are the force carriers. Like gluons are kind of bosons. I know it will. I'll explain you. Don't worry. Okay. So I hope this is fine. So there is something very important called parity violation. So what is parity? So something that tries to that should be in the same state or the energy level, but violation means that which comes to become the opposite of that, right? Which violates the parity, like which goes in some other state. So if you can read this, I don't know if you will be able to understand. I think after I'll be explaining you parity, then I think you'll be able to understand. So, and also parity violation, we can start with this, that if you have ever looked into the mirror, you might have seen one difference, which is that your left side appears right and right, like left of your side appears right and the opposite, right? So, but have you ever thought of the physics laws that suppose you live in one universe, and if I keep a mirror in that, and will the physics laws be same in the other universe? So this is what physicists thought, that and this is how the parity thing came into everybody's mind, that will the laws be same? And there were several experiments done with this parity and parity violations. So if I talk about our right-handed system and left-handed system. So we do some parity transformations. It's nothing. It's like easy transformation. Suppose you are going in plus z, and and there is some law which I have defined. And again, if I do it at minus z, then will the law be same? So transformation, parity transformation in mathematics is just like making the plus r coordinate to the opposite. And how will the laws change? So here I will talk about Wu's experiment, or Madame Wu was a physicist. She was a brilliant physicist, and she came up with the proof of that in beta decay. Just listen to it carefully. That in beta decay, there is some parity violation. So if I explain the Wu's experiment, uh, so what she did was she took some cobalt 60. That's why it's written here, cobalt 60. So in Wu's experiment, took the atom like cobalt 60, and under some magnetic field and some setups, she made the spin of the cobalt in the alignment to the direction of the magnetic field. Like it is aligned, is this in this? It was aligned in the same direction to the magnetic field, right? See, somehow maintain the spin. And also in beta decay, if we conserve the charge, we will and everything, we will see that in the product we will be getting uh, electron, of course, that's beta rays, electrons plus anti-neutrino. And also this thing I'll not get that much deeper, but what we defined as parity, and in coordinate system we define some of the particles which can be right-handed or the left-handed. Like just how we give directions, like we all know that for humans what is right and what is left. Similarly, for coordinate system we define what's right-handed system and what's left-handed system. So there are particles which are anti-neutrino, which comes in beta decay. So it's experimentally observed that anti-neutrino is left-handed. Sorry, anti-neutrino is right-handed. So, but the main thing is that if I apply conservation laws in Wu's experiment, then simply, like in simple terms, no need to be like get confused. So if I apply conservation laws, then we are getting some anti-neutrinos which can be in either way, like either left-handed or right-handed. But in nature, it has been observed that anti-neutrino can only be in one particular hand system, right? So this how it violates that electrons were supposed to be coming from either of the directions. Like if the spin is in the direction of the electron, or electron can be in the direction opposite to the emission of electrons can be in the direction opposite to the spin. But through this experiment, she got only one thing, only one value. What is that electrons is always coming to be in one particular direction, not the other direction. But if we apply charge conservation, then the other direction was also valid, but we were not getting that. So this is how it violated the parity and the conservation laws. So this was a major breakthrough in proving that parity violation in beta decay. So mainly this was all about this particular topic, which is the parity violation. So, and also, if I talk about parity, then there is called CP. You might remember this CP, that what is CP violation? So, CP again, it is charge parity violation, and we'll be again studying it now in some of the slides. So CP is just charge parity when there is matter and antimatter asymmetry, then we call it CP violation. So for now, I think you should just know about this parity violation. This a brief through that parity means what, and how has it violated that the results in one coordinate system which we are obtaining, it should also come in another coordinate system, like which another coordinate system, it means just the reflection coordinate system, right? So but we are not getting that. It is simply that in one coordinate system, if we are getting some of the products, in other coordinate system we should get the similar products, but it is just violating that. So this is what parity violation is. So I think you can understand this now a bit. So here is one more thing. Maybe you can read. And I'll see the chats if there is. So spin in one direction means that, yeah, so actually that was the experiment, right? So she aligned made the cobalt spin align in direction of the magnetic field. And again, see, we have defined right-handed coordinate system and like right-handed system and left-handed system, right? So again, according to charge conservation laws, electrons can come either in the direction of right coordinate system and the left coordinate system, right? Why can it not come to the other coordinate system? So this is what it's. I know it's a bit hard to grasp it now, but I think you'll understand. So since we are getting two things, so it can either come from left or right, because conservation laws are saying that. Okay. So that's why we are defining the directions that spin is in particular direction. Okay. Suppose in Bohr's experiment, I'm explaining it again. So that spin thing, that spin is in one particular direction. Okay. So but electron beams can come out of either direction according to conservation laws. But this didn't happen. Only one thing happened. Electrons were coming opposite to this spin in particular direction, in one direction. So that is why it violated the parity law, right? So yeah. So for you, why is it called quarks?
If you want,
There
I
is,
can just step in and explain that
yeah,
a little bit better. So,
okay,
see, we've observed parity violation in beta decay. That was Bohr's experiment, right? So,
yeah,
when you, I mean, generally when you talk about parity, it's whether your coordinate system is left-handed or right-handed. As in, if you have x cross y, is that z or minus z? That's what you generally mean by parity. Now, when you're looking at particles, we talk about something called their helicity, which refers to whether so a particle has some spin, right? And any whenever something is decaying, there's a direction to the velocity, direction to the momentum. So when you're talking about it having a positive helicity or a negative helicity, it's whether the spin is in the direction of the velocity or opposite to the direction of the velocity. So that's how we define particles as being left-handed or right-handed. If your spin, as in the direction of the spin, is in this generally when you talk about angular momentum, right? The angular momentum vector is given by your right hand thumb rule or whatever. So if the angular momentum, if the spin vector is in the direction of the momentum of the particle, then it's a right-handed, and if it's in the opposite direction, it's a left-handed particle. Now the thing is that whenever you're observing the decay of any of like when you're observing beta decay, at the end your angular momentum needs to be conserved, even linear momentum needs to be conserved. Like any decay obviously needs to obey the conservation laws. So your this direction of the spin of the electron, right? But you're observing something. That's what I'm coming from. The direction of the spin of the electron and the direction of the spin of the neutrino need to be opposite for them to be conserved. So when we measure the spin of the electron, we can measure indirectly the spin of the neutrino as well. So what we've observed is that we only get right-handed neutrinos. S mean by spin in quantum level. Wait, I'll get to that. Yes. So in the end, the spin needs to be conserved. The helicity needs to be conserved. You can't just add random angular momentum out of nowhere, right? So you measure the spin of the electron, you find the helicity of the electron, and so you'll obviously know what the helicity of the neutrino produced on the decay is as well. Like obviously this will need you like you'll need to sit down and work out the conservation laws by get your hands dirty. But in the end, we find that you only get right-handed electrons in beta decay. It's not that left-handed electrons don't exist, but any experiment that we've seen does not give you right-handed neutrinos. You always just get that to be violated, but uh, it is. So that's a problem of sorts. As in, not a problem. It's very important, but that's the confusion that arises over there. When you're talking about S meaning spin in the quantum level, so spin is, I mean, um, there's this famous quote by someone is like, if you want to imagine the spin of an electron, think of a ball that's spinning, except that it's not a ball and it's not spinning. So it's an intrinsic angular momentum. There's no actual spin. It's an intrinsic angular momentum held by uh, the electron. You can think of it as it actually spinning at a naive level, but to intuitively understand it right now, but that's not actually what it is. Just keep that small caveat in mind. And when you're referring to the quantum level, that's just as in when you solve the hydrogen atom of any system, at that point, spin is just another quantum number that comes into the picture because of Pauli's exclusion. I'm not sure what you mean by what if that symmetry is broken, or for all we know, the spins could be superposed. Yeah, the spins could be, but we always end up measuring the right-handed ones, like 100% of the times. It's max. There's a maximal violation over there, not just a little bit of a violation in beta decay. Like that, we observe parity violation in other systems and CP violations as well, but in beta decay, there's maximal violations. You just all of the times you get right-handed particles, right-handed electrons. We measure the spin by studying the behavior of the electrons in a magnetic setup. So depending on the spin, it would turn towards a different direction, right? I'm sure you guys did that in J or whatever. You have a particle with some velocity, and there's a magnetic field. You see which direction it goes and measure the radius, etc., etc. So similarly, there will be an interaction between the spin and the magnetic field as well, and you can, depending on the direction of the deviation, you can measure the spin. Okay. Sorry for the interruption. Right back to you, Anushka.
Yeah, okay. So yeah, so next it comes hadrons, baryons, and mesons. So I'll be explaining it, and there are more particles, leptons. But before that, let me open one model. Yeah, so this one. Are you able to see it? Is it?
Yep.
Yeah, okay. Yeah, so particles, if I talk about matter and forces, so now we are not talking about forces, we are just looking at the matter. Later we'll see the forces. So yeah, so we talked about, like, if we talk about fermions, then fermions are the particles with the half integer spins, right? So half integer spins, which means they will be having spins like 1 by 2, 3 by 2, 5 by 2, like that. And again, if we divide it into two categories like quarks and leptons, then we talked about quarks. And leptons, again, is kind of fermion, and we are familiar with electron as a leptons. So leptons are also six. So there are six kinds of types of leptons. So tau, muon, and electron. These are charged leptons. So these three are charged leptons, and these are uncharged. So again, if I talk about three terms which came, that hadrons, baryons, and again mesons, then hadrons are not fundamental particles, which means, I mean, fundamental in the sense that it is not the smallest unit. The smallest unit are the quarks. Hadrons are made of quarks, right? So if I talk about hadrons, again, we it is divided into baryons, which means which are made of odd quarks. Or if I talk about three quarks, then we know proton and neutron. So of course, protons and neutrons are baryons. So since these contain odd number of quark, which is three in the case of proton and neutron. Again, for mesons, these contain one quark and one anti-quark. So some examples are pion and kaon. There are more examples. So for leptons, fermions, this chart is very important. Then again, I'll say that these are charged and these are uncharged. Now, if we get back to our slides. So yeah, so again, hadrons, as I explained, these are not fundamental. Okay, so these are a combination of quarks, of course, held by strong interactions. And this is what these are the examples of bosons. And if we come to leptons, then there is something given called quarks versus leptons. So again, there is color. So color I'll be explaining you later, because you need that concept in strong force, that what is color. It's not like usual color, that why it is red, so it should be some reason, but there is no reason that why quark is red, blue, or green, like that, what you are thinking. But again, leptons have charge, no color, and also integral charge. And if we talk about mass, then you can yourself compare the quark mass, and suppose electron is the lepton and its mass so less. So again, these are uncharged and charged leptons. So we have again come to a very important topic, which is types of statistics. So, of course, in statistical physics, we get to know the real concept of like particles, its motion, its movement. Because see, we know that like air is made of so many particles, so we cannot take one air molecule and we can observe its motion like that. It's very tough. Actually, we don't need to. We have that statistical physics and uh, different distribution laws, so which can tell about the motion of different particles. So here there are two things, which are Fermi-Dirac statistics and Bose-Einstein statistics. So first of all, that you should keep in your mind that Fermi-Dirac statistics are obeyed by the particles which have half integer spins, like fermions, right? That's what I have explained. And these particles also obey Pauli's exclusion principle. So as you know that what is Pauli's exclusion principle, it is that all particles, no more than one electron can be, like if I talk in terms of electrons, can be in the same energy state as the other. No, more than one particle can be at this same energy state at some level. So it follows the Pauli exclusion principle also. I think somebody is messaging about I am not added to MS Teams. Can you just a minute? I think So anti-quarks, somebody has asked. Okay, so anti-particles, I'll be explaining about anti-particles. So yeah. So in Fermi-Dirac statistics, just I explained that it should obey the Pauli's exclusion principle, and also fermions have half integers spins, and in and in Fermi-Dirac statistics uh, lead to very weird objects of this universe that we should think about. We should see its graph. What it's in statistical physics, we see its graph and we obtain so many things. And in universe also, it has led to the a- answer of why white dwarfs or neutron stars e- exist. So, and also how can a star collapse to a dwarf, or a neutron star can go to collapse to a black hole. So these things can be explained with the Fermi-Dirac statistics. And also there is one more thing called anti-symmetric wave function. I'll be explaining both anti-symmetric and symmetric. So first, if I come to again Bose-Einstein statistics, so these are obeyed by the particles called bosons, which have integer spins like 0, 1, 2, 3, 4, like that. And also, just like I explained you earlier, that these are the force carriers. So again, somebody was asking that what are gluons or something like that. So I explained that gluons are also the force carriers. But force carriers for what? When some force, like strong nuclear force, acts, then the particle, the force carriers we talk about is gluons. And if we again deal with other kind of forces, suppose electromagnetic force, then we called about the carriers photons. And again, if we talk about weak nuclear forces, then talk about W and Z bosons. So again, we will be dealing this in the forces, but this is what it means. So symmetric and anti-symmetric wave functions. Now, in multi-electron system, suppose you have some psi, which is a function of R1 and R2, and and if you change R2 to R1, okay, suppose psi is a function of R1 and R2, then which is equal to again psi, which, which is a function of R2 R1. So, which means that its psi remains constant, it remains the same, even if you change some coordinates or something like that. So, which shows the symmetric wave function. So, these symmetric wave functions are seen in bosons. An anti-symmetric wave function, if psi is a function of R1 and R2, and like psi R1 R2, and if you change it to R2 R1, then a minus sign appears, right? So if psi R1 R2 is equal to minus psi of R2 R1, then we say that it is anti-symmetric wave function. So these are the statistics. We will not get into the deeper mathematical, like in proving the how the expression looks like, the probability density and all. So it's just the theoretical thing that we should keep in our mind. So again, we'll not see that expression, but those who are interested can see, or I can send some PDFs for how do we derive the energy states in Fermi-Dirac statistics and Bose-Einstein statistics. So yeah, so here comes a very important topic, which is the fundamental forces. So of course, forces are very important. So without forces, particle will, of course, wander around here and there. So in quantum mechanical model, or in, if I talk about microscopic world, so we talk about major three forces, which are strong nuclear forces, weak nuclear forces, and also electromagnetic forces. Now a question comes that our favorite force, gravity, why is it not there? So maybe I'll talk about it. We talk about it. We do talk about gravity. But so maybe we can talk about it a bit later. But main three things we'll mention, which is the strong nuclear force, the weak nuclear force, and the electromagnetic force. So yeah, so this is the matter diagram. That's yeah. So we have come to, and also remember, I have talked about the force carriers, right? I have talked about the how the force is transmitted by particles called bosons, right? That boat example, do you remember? That how you are standing on a boat and some person is throwing some heavy ball towards you. So this kind of energy transmission takes place through some particles called gluons. Okay, so gluons are basically nothing, but the force that is transmitted through some carriers, we need gluons, right? So this is what gluons are. But this is for strong nuclear force. Force, these carriers are gluons. And again, if I talk about weak nuclear force, since we're talking about force, it is W and Z bosons. And for electromagnetic force, it is photons, right? So strong force. So what is strong force? How strong is strong? Uh, how can we define how strong force? And here the question might come in your mind that why are we comparing it with electromagnetic force? Okay. So let's suppose that strong force, strong nuclear force, if I talk about, let's say it is just a bit stronger than electromagnetic force. Just suppose, what will happen? Why can it not be a bit stronger than electromagnetic force? So see, the answer is that uh, answer is easy. Since the atoms, the protons, which are being holded, like if I talk about uranium and all the heavier atoms, which has 92 protons and more protons, so these are being held by a very strong force, which we call nuclear force, right? So if electromagnetic force would have been there, then that protons would not have been together, because we know the range of electromagnetic force and it's so weak. No protons would have been bound together, no atoms would have been stable if electromagnetic force would have been there, right? So that's why we need stronger force, which means a way stronger than electromagnetic force to hold that many protons, of course, in heavier atoms. So it's way stronger. So that's why the concept of strong force is very important, that how strong we define to, like, with respect to what, right? So yeah, it's way stronger. And also there are some of things written, some unification, wonderful like behaviors and color confinement. So I'll be explaining everything in this now, in this under this topic, quantum chromodynamics. So Vanderbilt and Vanderbilt's like behaviors, which means that, of course, we know that nuclear forces are short range forces, unlike gravity or electron, like other forces, which are like infinite range or long range forces. So yeah, so nuclear forces are short range forces. So if protons come that much closer, then it comes into play, right? And also, what is quantum thermodynamics? It's a very important concept to like know about quantum thermodynamics. So I know that the force holding quarks inside nucleons works little differently. Okay, so and first of all, we should know about the charge. No, it is not that charge which we know, that positive and negative, and then positive negative attracts each other, negative negative repels, and same charges repel each other. No, it's not like that charge. We define here strong force charge, which is known as the color. That is what color which is being given. It is a strong force charge, which is known as the color. It is different. It's not like the normal color. It's just different, because I have already told that physicists give some weird name. So, okay, colored is one of the weirdest names for it. So it's a color charge. So we define charges at RGB. So there are three charges actually, unlike in electromagnetic force or in other like classical physics. physics, we electromagnetic physics, we talk about two charges, positive and negative. So we define three charges here, which is the color charge, which is red, blue, and green. So it has nothing to do with the color and the charge. It's just randomly like taken that red, blue, and green. So this is how the particles are governed by color charge. So this comes under the quantum chromodynamics concept that how RGBs are being like given the name of strong force charge. And also I have talked about the ranges that how mesons and gluons, like gluons are for very strong nuclear forces, and it has wonderful like behavior, which means like if I talk about the short range behavior. So I think these are the basic things under strong forces. So I'll be talking about the unification and all a bit later. So now we have come to weak forces. So think
Couple of questions, Anushka. Can you repeat about symmetric and anti-symmetric wave functions? And another one asking why there are only three generations.
three generations. Okay, so we're talking about these three colors, right?
No, as in three quark or three Lagrange generations.
Okay. Yeah, so the one thing which Anita Jan has written that 100 times more than electromagnetic, yeah, that's correct. And also, yeah, like simply like symmetric, and why strong force is strong range, why not long range? Okay, so like because it comes into play in that when protons are much nearer. If protons are far apart, then nothing comes, right? What happens if protons are far apart? That then that nuclear force doesn't come into play. So short range, which means in some minimum range, it comes into play when protons are closer in some closer sense, like you might have understood, right? So that's why it's called short range, unlike gravity, which is the long range forces, right? So even if like electromagnetic force, positive or negative, even you keep a distance apart, they'll repel or attract according to the charges. But it's not like with the nuclear forces. And about the symmetric and anti-symmetric wave functions, like similarly, what I have explained that psi, if we change the coordinates, that what is the effect on that psi wave function of the system? If we suppose define psi as something which is dependent on R1 and R2, okay, these are two variables, suppose R1 and R2. Then if we change the coordinate, if we swap it to R2, R1, then psi remains the same, which means that is symmetric, right? Symmetric all over the range. So so that's why like it's symmetric, and if the negative signs appears, negative sign appears, then it's anti-symmetric wave function. So this basic thing, I'm not going into that deep. So it's like the mathematical thing which I explained to you, right? Why strong force exists between proton and neutron? Why not protons and electrons? So see, we are talking about inside nucleus, right? Inside nucleus, there are not electron inside nucleus present. Like if I talk about nuclear physics or nuclear thing, then protons are there with neutrons inside the nucleus. So that's why we are talking about proton-proton repulsions, which is being held by the strong force called nuclear force, right? Not electrons. So I'll be so there is a doubt forum, I think. So you can also ask questions in that. I'll be answering maximum question here also. Otherwise, you're free to ask any of the questions. Later also I'll answer. Why do same charges repel? Okay, that's a very, now I think you have to tell me why do same charges repel? So I think it's a law of nature, right? Or something, like many things that we should leave it to nature itself. Then physics becomes easier, right? So I think we should continue. The three generations have been like this is how, yeah. So yeah, so also this is how we get through, like we have observed and through experimentation we discovered that many fundamental particles, and we have kept these particles under same properties and same generations. So that's why there are like three mainly categories, not categories or generations of tau, mu, and electrons, because these are charged. These are kinds of leptons which are charged, which are three particles which comes under this charged leptons. So that's why we get three categories. And also through experiments and observations, we have come through this. In a proton have different colors. Well, again, up quark and down quark, these can be of like any color, but RGB should dominate. Like actually, it's again a bit confusing concept. So these color can throughout the time, if you study deep about quarks, then throughout the time these colors can change RGB, like within themselves, but it has to be only three valence quarks in protons, if I talk about protons, so that the we can similarly like explain that why protons are colorless, or why do we define it as white, so that if we combine these three colors RGB, we get one thing, one color, which is white. So something like that. So it's a bit confusing concept, but so I think it's related to, yeah, so it's related to like that. So like I think I should continue teaching it. So again, here comes one more thing. So yeah, now weak nuclear forces. Like if I talk about weak nuclear forces, okay, so the first thing appears is that radioactive decay. So we'll not directly jump to radioactive decay. So before that, I'll be explaining you many things. As I've already explained you that force carriers and weak forces are W and Z bosons. Okay, so here is very one more important thing, that quantum flavor dynamics. What's quantum flavor dynamics? So again, it's a kind of concept which is being observed, and also many experiments where like undergone scientists have undergone many experiments. So what is quantum flavor dynamics? So if we talk about suppose take top top quark, okay, and if under strong force condition, if it emits uh, suppose, or if you take electromagnetic conditions, first of all, simply. So if you take some electromagnetic condition, and if you take a top quark, and if suppose it emits a photon, right? So under electromagnetic conditions, it emits a photon, then what will happen? What will happen to the final end result? Then I can, then like it's observed, and we can easily say that the end result will be that it is again going to be the same, the top quark only. Okay, so if top quark is there, and if it emits a photon, then the final end particle which will be getting will be again the same particle, the same identity, which is the top quark. It is being observed. And also photon is has no charge. Then again you can say that I think it is a violation of some laws or momentum laws. We can talk about physics laws. Then even if we talk about, we can say that in electromagnetic conditions there is no change of the identity, because the top quark initially was top, and after emission of a photon it is going to remain as top. Similarly, when strong nuclear forces, what happens in the strong nuclear forces, that top, suppose we have a top red quark of red color, then under strong nuclear forces, by emitting like particle, its color might change, right? Suppose that red top quark can become a blue top quark under the strong nuclear force attraction. It emits some particle, but again its identity is same because it is a top quark only, right? That color charged difference can go, but it is the same particle, its identity is same. So in what happens is that in strong nuclear force and in electromagnetic interactions, what happens is that if we take any quark, by the end, even if we even if it emits particles, the final particle which we obtain, its identity is the same, but something weird, something opposite happens with the weak nuclear interactions. So for weak nuclear interactions, so again if I talk about for yeah, so for weak nuclear interaction, we talk about W and Z bosons. So Z bosons, what happens is that for Z bosons, it's uncharged, and with Z bosons, nothing is happened, which means the top quark, even if it emits particles, it remains the same top quark, which means that in with Z, the identity remains the same. But for W bosons, something weird happens. What happens is that the top quark changes to some other quark, some different top to quark. Some other particle can change into like some neutrino to anti-neutrino, something like that. Some different things happen. Or bottom quark can change to strange. Something different happens with W bosons. So this is being observed. This is only limited to weak nuclear forces, and also when W is emitted. Okay, so this is being observed and also experimentally confirmed by different physicists. And so this is called flavor dynamics. So physicists again call it some by some weird name called flavor. So that's called that flavor thing comes, which means some change in flavor identity comes. So that's why we link it to the weak nuclear forces. And also you can say that why with Z, since it is also a weak nuclear force under it, Z also comes, then why with Z bosons it does not emit anything? First thing is that you can say that Z is uncharged, but I think a better thing is that there were combinations. Okay, that was in experiments the scientists took. Like they did experiments with Z bosons. That suppose there is a top quark and it emits Z bosons, and we get some different quark, but that is never going to happen. It is near to impossible. So it's because of the experiments they never got the result. So that's why we also say that with Z bosons it is never going to happen that we will get a different quark of different identity. It only happens with the W bosons. So this is what the flavor dynamics and change the flavors of the quarks. This is what it is all about. And also there is a P and CP violation that if I talk about some P and CP violation, then again I have talked about that CP is the charge violation and P is the parity violation. And before that, I'll also talk about the electroweak theory. So what does electroweak theory means? So electroweak theory is nothing but it talks about the unification of weak forces and electromagnetic forces. So it talks about some unification of these two, and also we talk about weak isospin and weak hypercharge under this. So the main thing is that electron weak theory can be explained a little later when I'll be teaching about some other particle, very special particle. So that uh, you might know or might not, I don't know, but that's a really special particle that is included in the standard model. So so I think this is what it's all about. And also, since there is a parity and charge parity violation, okay, that's why we talk about radioactive decay, right? So since in radioactive decay or in weak nuclear interactions, there is a charge violation, which means that uh, for matter and antimatter. What is antimatter? So similarly, a matter which has, suppose I talk about electron and positron, then the mass is same for both, but the charge becomes different, right? So if it is E minus, then the other is E plus. So simple example for anti and matter and antimatter. So CP violation is that when there is asymmetricity in between matter and antimatter, which means that even if I take the reflection, the matter is not, we are not getting antimatter in the other hand. We are getting something different, right? So that is what this parity violation occurs, and this is the reason which which can be explained that why radioactive decay comes into play, right? Under weak nuclear forces, like weak forces. So again, like if I talk about this part, so this is easy. So electromagnetism, as you all know, uh, electromagnetic spectrum and of visible light. I think you are familiar with these things, so I'll not explain it that deeply because yes, I think you'll be knowing it. So of course, I've talked about it, it's a longer range, and also the Maxwell equations that talks about the fundamentals of that talks more about the electric and magnetic fields, and also how these equations can tell us to like can make us to solve lots more problems, resolve the problems related to electrodynamics, which is there. So, and also the electron particle duality. And also one more thing that we talk about that photons are massless and also its spin is one. And like because people are confused that how do we define spin or something like that. So just to explain that it satisfies with the consistency, like with consistency with the, it is consistent with the general relativity and also the quantum field theory. So this is how we define photon as spin one, and also it's massless, but we can also talk about the rest mass is zero, and does it have uh, when it's in motion, then we talk about its mass. So and also in electromagnetism we talk about various phenomenons, which is like easier to understand. Now, here comes a very important topic, which is gravity. Like, why did I leave gravity? And is gravity a part of standard model? No. Why was gravity not there? Can it be included? But what is graviton? And again, these things, why massless? And so, very important thing. Gravity is ridiculously weaker. It is super duper weak, and we don't know why, but it is really, I don't know how many zeros, one upon how many 100s should I include to compare with nuclear forces and other forces. It is very weak. So since it's too weak, so it becomes very tough to talk about in micro world. Like if I talk about nucleus, and protons, then in that, if we talk about gravity, then again it doesn't make any sense, because since it's too weak, and like we can almost neglect, but we should not, we must not. So that's why gravity. But the question we can answer, that why is gravity a part of standard model? So again, we can explain it by theory of gravity. So again, we can explain it by the theory of gravity, or like Einstein theory of gravity. So one thing is that, suppose you have a nucleus and you have an electron revolving, right? We have read it in smaller classes. Like if you have a nucleus, you have electron revolving, then one time will come, since electron is losing energy, so it is losing energy, so it will fall under proton. So similarly, Einstein gravity theory of gravity says the same thing, right? So which shows the parallel thoughts between the electromagnetism and gravity. So which shows that, okay, if we talk about electromagnetism in a macroscopic world, then we can also talk about gravity in the macroscopic world. And also one more thing is that, like in quantum field theory and in some quantum forces, we define for electromagnetic forces, we define something called photons as the carriers, as the particles, right? So again, for gravity, we don't do anything. So again, there comes a chance that, okay, gravity can also be discussed in this. So first of all, if we talk about quantum gravity, it's just a concept proposed due to these kinds of problems, that why gravity is not included, because since it's too weak. So in quantum gravity, we just assume that since gravity should be the part of standard model, if it becomes the part, then there should be some particle called gravitons. Okay, there should be some particle called gravitons. And also, since gravity is a long range, infinite range, gravity is an infinite range force, so gravitons should be massless. And also one more thing, spin too. So again, it's like bit confusing concept, that why spin 2. So just understand that, like for briefing, I would say that for it satisfies the conditions of general relativity and quantum field theory, just to remain consistent with this, then only we can thought of gravitons, right? If you can say that why spin is 2, why it's not 4 by 2, like 4 by 5 or something like that. But see, you have to remain consistent with the laws, because quantum field theories and these laws are the laws which we talk about recently in recent researches. So these things we have in our hands. So that's why, to remain consistent, we consider it as spin 2. And again, if the particle exists, matter, then according to various principles of quantum electrodynamics and other Dirac's principle, we'll be studying that. There should be some antimatter pair also. So anti-graviton also be defined. Since graviton is there, its antimatter, which is anti-graviton, is also there. Okay. So this is how I explained about, yeah, gravity. That why, what is gravity, and since you know the concept, what is gravity, that Newtonian concepts and Einstein's concepts of like distortion of space-time work with the Hebbier object, that is, this is Einstein's concept. So that's what it was all about. But the main thing is the unification. Can it be happen? Can I? Yeah. So can it be happen? Can I talk about unification of various forces, or can we define a grand unified theory? Yes, there is one grand unified theory, one model, which talks about the unification of all kinds of forces. And it's predicted that we can unify, but again, we cannot say that it's 100% valid. The unified theory, it's not 100% valid. And also there is one more thing that comes in our mind, that when we talk about grand unified theory, the theory of everything. So I think there is some kind of competition or something like that between two. And also we don't know what is 100% valid. So the clear picture of unification is still not there with us. But one more picture which we talk about, so we discussed about quarks, we discussed about leptons, we discussed about force particles, like bosons. But I think there is some special particle which is missing, something which can explain some weird thing. So yeah, oh yeah, so that's oops, the Higgs bosons. So yeah, so some like I think it's an article I read somewhere. So it's called the God particle. So mainly just because it gives mass to the other particles, but the concept is not that easy. So if I talk about its history, then Higgs bosons that Peter Higgs earlier predicted that since there are some particles whose mass was too heavy, some particles whose mass was like of moderate level, and some particles were almost massless. So why was it that? To explain, to come up with something like that, Peter Higgs proposed one theory that there should be some interactive field that would be giving mass to some of the particles. That's why we get, and when the mass, the particles which interact more with the Higgs field, right? We are just talking about Higgs field. Now don't think about Higgs bosons. We're talking about Higgs field. Then we'll come to Higgs bosons. So Higgs field is something like a kind of medium that gives that is giving mass to some another particle. So those particles which will interact more with that medium, that will be heavy. Okay. So again, there is one more sentence that heavy particles interact more with Higgs. Is this wrong or correct? Or the particles which interact with Higgs become heavy. So I think the second one is correct, that particles which interact more and more with Higgs field becomes heavier. And also, just like in gravity, we define gravitons, there is some carrier, right? Some unit, some fundamental particle of the field. So, similarly, to define the smallest unit of that field, there we talk about Higgs boson, that particular particle that is associated with it. So that's why, firstly, he defined Higgs field, and again we got Higgs bosons, and also, yeah. And also for Higgs bosons, we got confirmation in July 2012, in some experiment conducted at CERN. We got the experimental verification of Higgs field, and that was a major breakthrough. And in 2013, Peter Higgs and one more scientist shared the Nobel Prize for Higgs bosons. So that's one more thing. So again, there is one more thing for the Higgs field, which I can explain, which like I explained you about the electroweak theory, right? So let me search for it. Yeah. So these electroweak theory, what is that? So again, I can explain it with the Higgs field, because without Higgs field, it doesn't have any meaning. So electroweak theory, we talk about unification of theory just because we talk about Higgs field. Because see, if I talk about weak nuclear forces and electromagnetic forces, we know that electromagnetic force is a strong force. Weak nuclear force is a like nuclear force, a short range force. Then how this unification is coming? So since weak nuclear force, for weak nuclear force, Higgs give mass to weak nuclear force particle carriers. So that's why we talk about the electroweak theory and unification, right? So it's due to the Higgs field we defined this, the electroweak theory. So now here comes the whole picture of all, where we have in the standard model, we have included the force particles, leptons, Higgs bosons. Wait, let me show. Yeah. So I think this is the perfect slide, I'll be sharing this with you. For forces, bosons, and photons, gluons, and okay, gravitons I have included, but again, there's a question mark here with the gravitons. Just keep in your mind. And also, here comes a very important concept of antimatter. So, yeah. So, please don't get scared by seeing this equation. I'm not going to like go deeper into that mathematics, but similarly, like, but I can say that Paul Dirac's equation is a like relativistic equation for electron, which shows that for with matter, matter pair also like matter and antimatter pair exist. For a matter, there can be a given antimatter. So why antimatter I'm talking about? Because and what is antimatter? Just like I have explained that for electron and positron, suppose if we take one example, that the charges will be just opposite and the masses will be the same. So I think this comes through the solution of these equations and negative energy solutions. So there's a very good thing. I was looking for copper and I found gold. So this antimatter phenomenon can explain a variety of things. And also we can see through the parity change through matter and antimatter that is it satisfying this or not. So through parity transformations also we'll see. I'll not get into that deeper, but actually its solution comes to be like that, that matter and antimatter exist in a pair. This was Dirac's equation. There is one more thing that you should keep in your mind. So, like I read about something called Dirac's thought on having three fundamental particles. So actually, this thing didn't become that famous. So what happened is that Dirac thought of some particle that is electron, proton, and also some particles called dion that could contain electronic charge and also magnetic charge. So, but some of the theories didn't satisfy. I'll not be explaining that deeper because it was not accepted. So some of the theories didn't satisfy, and also it was not that famous to be discussed. And also since we have come to be, we have come with a better model now, and of course today standard model is being accepted. So we don't talk about it like that. So that dion was never found experimentally also. So that's why we stopped talking about this. So again, he talked about protons, neutrons, and some particle which would have some magnetic charge also and some electronic charge also. But that particle was not found. So we don't talk about the Dirac's thoughts of three fundamental particles that much. But this also was proposed by Dirac. So finally, we come to this scenario where all the particles are mentioned, and this is my standard models of elementary particles. And so can you say that it's a complete picture now? So I think my part of this is over. So maybe Vivan, yeah, will be taking it after now, after this.
Hello. Can you enable sharing for me? I can't share my screen.
Yeah. Just a minute. Let me that option is not coming. Just a minute.
Oh, if gravitons aren't mass less, then they would attract themselves. Like by, I mean, you don't see photons interacting with themselves, right? They don't have any charge. So you don't have random photons suddenly interacting and giving rise to something else. So that's the whole thing that you see about. I mean, otherwise, you wouldn't be able to see anything if the two photons just going through. You're seeing a chair at one end and the table behind it, and if they interacted within themselves, you wouldn't be able to see them as two separate things. So photons can't interact because they have no charge. And similarly, even if gravitons were self-interacting, then anyway, see, we don't really know much about gravitons. Like, no point discussing a lot about them because they're a hypothesized particle at the end of the day. There's nothing we've
Yeah, I
observed. We just have some constraints on its properties, and it being massless is one of them. It having to be a spin to particle is one thing. Okay, yes, I can try this. Thanks so much.
I think I have given you the access. Can you just
Yeah, yeah,
try
I
sharing
got
this?
it. Is this working?
Yeah, yeah, it's fine.
Okay, so this is why you left off.
Yeah, so
So again,
from here.
just rush through. You can't see like I have a. You can see the whole screen, right? There's a dialog box. There's a pop-up mute thing on my screen. You can't see that, right?
Yeah, yeah, yeah. We can see the whole.
All right. So this is where we've ended so far, right? You have um, three quark generations, three electron generations, their corresponding antiparticles. You have your gluons, which mediate the strong force, the photon for the electromagnetic, and the massive vector boson, which as I said, W plus and W minus for uh, the weak nuclear force. Obviously, there's the Higgs, which is a scalar particle giving mass. What you've studied right now, gravity is not included, graviton's not included here, won't be included anywhere because it's not exactly a part of the standard model. It's just one hypothesized way to quantize gravity. So this is all we know about the standard model, every particle that we think exists. Everything else is some of the other composition of this. Now, when you look at any interaction, um, when you need to study any interactions, any decays, there are certain rules, certain symmetries, conservations which come into play. And I think over the next few slides, we'll look at that first. Okay, so yeah, just an aside before that, you saw that there are three color charges essentially, and the corresponding anti-charge. In the sense that when you look at an electromagnetic thing, there is only one charge. The charge can take two values, as in a positive and negative one, but there is one charge as such, right? So in a similar way, for the strong force, you have three color charges, red, green, and blue. Again, very important that these are not actual colors in any sense of the word color because the sizes of these quarks are unimaginably smaller than the wavelength of visible light. So there's no color at all. It's just a mnemonic that we use that physicists have given it just to get a better idea. Because I mean, we're running out of things to name things at the end of the day. Physicists have a very arguably nerdy, arguably very funny sense of humor, depends on whom you ask. I would arguably very funny, but jury is still out for a lot of people. So one question that I think someone had asked is why color charge is why different RG and the quarks in a proton. So okay, when you looked at Fermi Dirac statistics a few slides ago, and one thing that all of you would have studied at some point, or at least heard about, if not studied, is like Pauli's exclusion principle, right? You can't have um, a bunch of particles with the exact same quantum numbers in the same state, right? So there needs to be something different. That's why, in one shell in an atom, you have a spin up electron and a spin down electron. You can't have two spin ups. And similarly, when you look at the valence quarks in uh, a proton or a neutron will need to be the like if color did not exist as a quantum number, then there would be those three quarks would have exactly the same quantum numbers would be in the same state, which is not something that is allowed because by for Dirac statistics. So that's why color was initially hypothesized and that they just said something, and then of course over time we've gotten a bunch of reasons to confirm that okay this exists. We have um, like most of these come from when you study the rates of certain decays, right? Um, if you had no color as opposed to if you had color, there is a scaling factor involved because the probability increases threefold, right? So we've measured those scaling factors with color indices, and we know for a certain that at any energy scales that are accessible to us, which I mean the highest that LHC right now is about 15 TeV, like the center of mass energy scale of 7 TeV, so you double that. Which is very high. The heaviest particle we know the top is, I believe, around 2 GeV or something. I don't remember the numbers, but yeah. So we know for now that there are only at any accessible listing three colors, and as Anushka mentioned before, red, green, and blue give white, and red and anti-red also give white. So this gives you two different types of hadrons. An odd number of hadrons, an odd number of quarks make up baryons, and when you have an even number of quarks, they call mesons. Now, baryons obviously are fermions, and mesons are bosons. So even when you were looking at the strong force earlier, mesons are also force carriers because they're gluons, because they're bosons, right? So gluons, as you saw, mediate the strong force inside the nucleus, right? But if you remember, there was a van der Waals like behavior mentioned where even between two nuclei, as in there is, sorry, inside the quarks, but even the quarks inside a nucleon, sorry, inside a nucleon, the gluons mediate the quark field and compose a proton or a neutron. But at the end of the day, you still need all those protons to be bound together inside a nucleus, right? So over there, the mediation is not by gluons, it's by mesons, which are essentially two quarks. So constantly, because of the insanely high binding energy over there, there's a constant production of quark anti-quark pairs, which mediate this force. Like so, when you say that there are three quarks inside a proton, in the sense that there are three valence quarks, three unpaired quarks. Apart from that, there are constant uh, pair production keeps happening, annihilation keeps happening because it's just a lot of binding energy that's there. At some point, it manifests in the form of a quark anti-quark pair, then exchange with another nucleon, and so on and so forth. All right. So a lot of I mean, right now, see, you've had a very qualitative picture, right, of anything that you're looking at. You'd think why three colors, why one charge for electromagnetism, and the thing is that all of this has something to do with symmetries. Um, can anyone tell me who the lady to the right is? Actually, Aminozer, correct. So, Aminozer came up with, she was a brilliant mathematician. Unfortunately, because she was a woman, she's often forgotten and pushed to the sidelines of history, but such is the patriarchy. Anyway, that is inside. Coming back, she came up with this brilliant, beautiful, and beautifully simple thing called Noether's theorem, which talks about symmetries and conservation laws. So, what it says is that any symmetry that exists in a system gives you some quantity that is conserved. So, when I talk about symmetries, what do I mean? Like here, you see time translation, space translation, but what exactly does that mean? say you write down the equations of motion for any system at all. Yeah. Now, this is a little bit difficult to understand in Newtonian mechanics, not as intuitive. It comes more intuitively when you study Lagrangian mechanics and Lagrangian Hamiltonian formalisms, but still, like, it should give you a rough idea. So when you write down the equations, whether your time axis is defined as t or at t plus a or t plus b, where a and b are any constant, that won't change the equations of motion. Like your equations of motions are independent of the starting point for time. If you have any such system where your Lagrangian does not depend on time explicitly, then it's symmetric in time. Similarly, if it does not depend on the x coordinate or the y coordinate, it's symmetric in that coordinate. And a symmetry along the x coordinate leads to conservation of momentum along the x coordinate. A symmetry in the y coordinate leads to conservation of momentum along the y coordinate, and similarly, time is energy. Now, you must have heard that, like about rotational translation. If there is no explicit dependence on the theta term, angular momentum is conserved, right? Because your system would be the same whether you look at it from a certain angle or that angle plus 90 degrees. If there is some spherical symmetry, angular momentum will be conserved. So now these three symmetries, which are physical symmetries that you can visualize and understand, are the basis. They're very basic ones, but there are a lot. I mean, these are all continuous symmetries. We'll look at discrete symmetries also later on, but right now, just looking at continuous symmetries as and when there is a continuous change that's happening, right? We're not looking at, like, it does not have to be discrete. So there is a continuous transformation which can take you from one coordinate system to another. Even if your coordinate system starts at, if your origin is at 0 or if your origin is at 10 centimeters or whatever, it does not depend on the coordinate system. These coordinate systems can be defined through a continuous transformation. Now, these symmetries are physical symmetries, and they give you conserved quantities that you are aware of so far. But there's another thing called gauge. Um, it would be very difficult to explain what gauge is like at this point of time. Like you need to have a certain bit of a mathematical background uh, in field theoretic concepts, but I'll try nonetheless. So you're not choosing a set of origins as you would be in time or space symmetries. You're choosing certain energy conditions. So when you solve the electromagnetic,
Just 1 minute.
sorry, yeah.
I think a few students are writing that they are disconnected.
Oh,
I am disconnected.
can you see and hear me?
Yeah, like it's fine for me.
Okay. So, whoever's disconnected, just try joining again, maybe.
Maybe you can try joining. Yeah.
Yeah.
So yeah,
Cool. I'll
fine.
just wait for like 30 seconds for everyone to rejoin. And okay. Yeah, no worries. As in, if you get disconnected, just try and rejoin. That usually solves all of this problem. Anyway, getting back to what was I talking about? Yes, you write Maxwell's equations. You try to solve them. You need to specify certain boundary conditions about the electric field. So you have different gauges. You must have heard about the Lorentz gauge or the Feynman gauge, and uh, where you say that the divergence of the electric field is zero, or you define certain boundary conditions, and the symmetry says that the final solution does not depend on the gauge you're choosing or the boundary conditions you're choosing. So there is a symmetry in the gauge. which leads to charge conservation. Of course, the math about this is like way beyond the scope of this talk, but you can look it up if you want. Just look at gauge symmetries and uh, most of the standard model is defined based on symmetries. Like this might seem like a very trivial thing, but we'll look at a little bit stuff um, in a while. So, all right. Um, Wait, how much time do we have, by the way?
So
Namaste.
actually we started late also,
Yeah,
so
so can we extend or
yeah, I think we have 1 hour at least because it's
an hour,
twelve
right?
thirty. So till 1:30 we can do, I think,
Cool, right?
1 hour.
So, cool. All right. So now the first three, four um, things you see over here, the first 4 points over here are approximate conservation laws and approximate symmetries, as in they're valid only in certain conditions. They're not general symmetries which are explicit. Actually, all of these are sort of approximate conservation laws, but we don't expect all of them to be approximate. So I'll just look at them one by one. Now, you just look at baryon number. So what's a baryon is essentially all the baryons that we'll talk about over here are made of three quarks. So of course, your protons and neutrons are the most basic, like they're the lightest baryons, but you have other baryons as well. You have the ions and so on and so forth. The lambda, the, the like right now we're looking at just up and down, but any three quarks can form a baryon, right? You can throw in a strange quark, you can throw in two strange quarks, whatever you want. Like, of course, not all of those lead to stable particles, but in theory, there are a bunch of baryons. So, baryon number conservation just says that at the end of the day, when any reaction that you write, the number of baryons on the left side and on the right side needs to be the same. Simple as that. Similarly, lepton number is that the number of leptons need to be same. Now, uh, baryon number and lepton number so far have been like we haven't observed anything that violates baryon number or lepton number, but we have very good reason to believe that it should be violated, which I will talk about towards the end of this when we look at beyond standard model physics. But uh, essentially, baryon number says that the number of quarks has to be the same. You can't, just have one quark come in from anywhere. And you can have one type of quark convert to another type, right? You can have a down quark changing into an up quark, or a strange quark decaying into an up quark, but you can't have quarks just completely disappear. So the number of quarks in the whole is conserved, but the flavor can change with a W plus or W minus. But lepton number, on the other hand, every individual lepton flavor is conserved. You can't have as in all of this I'm talking about is in the within the constraints of the standard model. You can't have a muon decaying into an electron or something like that. There are hypothesized beyond standard model decays, but as per the standard model, lepton number is conserved for every flavor. Now, strangeness also in strangeness is basically just the number of strange quarks which exist, right? So, a strange quark would have a strangeness of -1, and an anti-strange quark would have a strangeness of +1. Why it's like this? Purely due to historical reasons. Like, if we just name the strains the anti-strain, it will be swapped and be more, aesthetically pleasing and uniform, but just because of historical reasons, it's stuck. Um, so when you look at any stronger electromagnetic interaction, the strange quark will need to exist at the end. It can be a part of a different particle, but the strange quark will need to be there. So electromagnetic and strong interactions conserve strangeness. When you have a weak interaction, of course, your strange quark can decay into an up quark, right? That's a decay. It can't decay into the down quark because uh, you would need a flavor changing neutral current for that because the down and strange both have the same electric charge, which is impossible. So strangeness can change only when the weak interactions involved. Similarly, flavor also won't change in strong and electromagnetic interactions. Now, coming to the last three, they're the most important, or at least the most interesting symmetries which exists in the standard model, or in physics overall, not just necessarily the standard model. Charge conservation, which is C, parity, which is P, and time reversal, which is P. These three are distinct, they're discrete symmetries, as opposed to the continuous symmetries we discussed earlier with translation, right? Because here you need an irregular transformation to go from one to another. You can't have a continuous transformation which changes a right-handed system to a left-handed system. Now, parity, charge conjugation have been discussed by Anushka earlier, so I won't spend a lot of time detailing that because we're running short of time as well. But time reversal is essentially going from the universe evolving, you just say reversing the arrow of time. Now, initially, we are like everyone thought that C, P, and T would be individually conserved, but um, when like you talk about when Anushka mentioned Wo's experiment on beta decay for 168, that you saw like the weak interaction maximally violated parity. It's a complete violation. We don't have right-handed neutrinos at all. You only have left-handed neutrinos and only right-handed antineutrinos. So the weak interaction violated parity. Then after some time, you look at there's something called a neutral kaon. It has two states. You look at the decay of a neutral kaon or even neutral B meson. They oscillate between their two eigenstates, and won't get into the detail of that because again, the scope beyond the scope of this. But essentially, CP on the whole also needs to be violated, right? Like you can't uh, CP on the whole in the sense that you change every particle to one antiparticle and you go from left-handed system to a right-handed system. So CP violation is also a very important and very interesting property of the weak force. So now you look at this. You know that CPT on the whole needs to be conserved. That is something that we know because it lies at the heart of any quantum field theory. Any quantum field theory that violates CPT would not give you things like energy conservation uh, like Lorentz transformations would be violated. And so, I mean, we're almost certain that CP2 symmetry on the whole holds, right? So now, obviously, if CP is violated, then T symmetry also needs to be violated by the weak force on its own. But we haven't really observed it yet. We're looking for it, but we haven't found um, time level like T violations in the weak force. So, yeah. Global gas.
There is one question
Yeah,
like,
sure.
so
Uh,
does any combination of three quarks form a baryon?
I mean, it can form a baryon, yes. Can it form a stable baryon? Not necessarily. We've only, as in, there's no theoretical reason as to why it's not possible, right? But a lot of them don't have enough, like the say if you look at the top quark or the bottom quark, right? They're themselves so heavy that lifetimes of the top and bottom, especially the top, are so small that it does not have enough time to hydrolyze. So that's a very interesting, especially for the top quark. The top quark itself is so heavy and so unstable that it does not hydrolyze. So you can actually detect uh, a free top quark if you have that much of a resolution because it decays before it can hadronize and form uh, meson or a baryon with another one. So if you look at the first two generations, you have your up-down strain charm. Yes, you can form baryons with all of them, but not all of them are stable. You have, I think I mentioned it earlier. Look up the eightfold way, right? So there were The quark model initially was suggested by this dude called Murray Gell-Mann genus. So we looked at, like, I think a few slides back, there was that quote by Dirac about how three three elementary particles is too much. Or that was, I think, in the 40s. And by the 60s, uh, we had something called a particle zoo. As well. There were so many particles and so many hadrons which had been observed when particle accelerators reached certain energies that it was confusing as to, like, there can't be so many elementary particles, right? So that's when Murray Gell-Mann came up with the eightfold with the for substructure based on certain symmetries that we found. So all of these particles weren't even, like, this was something called group theory comes in. If you guys are interested, just look up group theory. Even a Wikipedia glance, or there's certainly certain books that you can DM me after this. I can recommend some books. Uh, Symmetries are exceptionally powerful, especially when it comes to particle physics, because not only have we explained the stuff using symmetry arguments, we even predicted the existence of a lot of particles. Like, for example, when you look at, Gell-Mann predicted something called a lambda, which would have to exist with certain properties, certain spins, certain strangeness, certain mass, based purely on symmetric arguments, because he needed the lambda to exist to explain everything else based on, uh, based on his work model. And obviously, cut to 5, 10 years later, we observe the lambda. So symmetry arguments exceptionally powerful. Cannot explain this enough. Especially for everywhere in physics, but especially here in particle physics. Group theory is a brilliant tool that we have. And so yeah, all of these quirks can exist, but not all of them will be stable. That was the take. Alright. Lepton number is also the Lepton number. Just mentioned global gauge invariance. All right. So yeah, I mentioned. Now, when I was talking about symmetries, right? So the when you look at group theory, it's essentially a group is a set of transformations cons- that conserve some quantity. Okay, there's a mathematical definition for a group. I won't go into that, but a group is the way you represent some symmetry. So, say you look at rotations. Okay, you have a 2D plane, you look at a rotation in that 2D plane which leaves the z-axis unchanged. So you have one angle theta that generates those rotations. So you must have heard something about um, the generators of angular momentum. I'm not sure if you might have just heard some random sentence here and there. Probably not, but I'm not sure. Um, anyway, so when you look at this symmetry of rotations in the 2D plane, you have something with groups called SU2. So it's a special unitary group in of dimension 2. In the sense, it's unitary. I mean, SU2 stands for the S is for special, as in it has determinant +1. Unitary is, the U transpose is identity. You know what a unitary matrix is, I suppose. Like the product of the matrix and its transpose gives you the identity matrix. Anyway, so there are a bunch of groups which are defined which lead to a bunch of symmetries. Now, there is something like, so based on our observations, there is a standard model gauge group.
Vivan,
Yeah.
your voice is breaking. I think it's not clear.
Is this better? I don't know.
Yeah, I think it's better. Like it was
Okay,
just in the middle, it was. Now I
cool. Okay,
think it's better.
cool, cool. Gayatri, I suppose, as in, if the issue persists, just try leaving and rejoining. And it's it's just funny how often that fixes things. Okay, particle physics for beginners. Look at Griffiths. That's the least mathematically rigorous one to Griffith's elementary particle physics. But again, you will need like some amount of a mathematical background to, you know. So if you're just interested in this as a pastime, honestly, Wikipedia is a pretty good resource. Like, just you want to look at it from a, like, if you don't actually want to study the math, just Google stuff, read, go down Wikipedia rabbit holes. That's how I first learned it years ago. I mean, obviously, if you want to properly study the maths, then Griffiths is a good book to start with. Where was I? Yes, the gauge group. So there's something. So the standard model gauge group is something that again we'll discuss in a bit. But essentially, there are a bunch of symmetries. Symmetries have some things conserved, and all of these conservations are, uh, a result of those symmetries which exist. So group that every group has a certain number of generators. So when you look at the gauge group, okay, I'll come to that later actually. Okay, we can already discuss that. Yeah, the strangeness. See, all of these particles, the pions, lambda naught was something that was just predicted by Gell-Mann, and it was also much later. But all of these particles you have, which the pions, kaons at that point was what motivated Gell-Mann to come up with the quark model because it just felt like way too many elementary particles to have. We spoke about CP vibrations. Yeah, so kaon oscillations come into this. So there are two neutral kaons, which is the K naught and the K naught bar. So the K naught has a down and an anti. So yeah, the notation here is like whenever you have a bar over uh, any particle, it's the antiparticle, corresponding antiparticle. So the kaon has the K0 has the is made up of a down quark and an anti-strange quark, and the K0 bar is made up of a strange quark and an anti-down quark. So you see the straight like you know when you take the charge conjugate of the K0, the down goes to an anti-down, and the anti-strange goes to a straight. Now, both of these particles exist in an eigensystem. Uh, like they exist in a mixed state, not as K0 and K0 bar, but as as K0 long and K0 short. They have two different decays. It can either decay into 2 pions or 3 pions. And it was expected that, the short one would decay into 2 pions and the long one would decay into 3 pions. But the there was a discrepancy in the calculated rate and the finally observed rate of decay. Like you also saw some 2 pion decays for the kaon with the long for the uh, K0L basically. So which is where we saw that CP needed to be violated and um yeah, I will go into that. Yeah, so weak nuclear force has violated almost every symmetry that we've expected it to conserve or expected to be conserved. CPT, of course, hasn't been yet, but CPT is not, you know, it's very, very unlikely that CPT will be violated because if CPT is violated, everything that we know about physics goes out the window. And that does not seem to be the case because we know a lot of things about physics. And for those to be true, CPT needs to be conserved. All right. Do you guys want a break? They want a break. This PT being violated. Yeah, so C is violated, PT on the whole would also need to be violated, right? Because CPT has to be concerned. You can go buy Kit Kats. Um, yeah, my hostel vending machine is also out of Kit Kats, unfortunately. Otherwise, I would have definitely. thought about. They haven't refilled it since yesterday. It's very sad. You can take a 5 minute break if you want. What's the time right now? It's 12:49, right? Yeah, 12:55 is when we'll start again. We finish by 1:30. And if you guys have any questions, I will take questions until then. But yes, you can just type out your questions. I think pretty sure you're all muted for good reason. But you can ask any questions here. I'd love to answer it. I'm just surprised you guys were like, still paying attention and asking questions to us. And I would have zoned out basically. So, like, good stuff, please. No, no CPT violation. All right. What do you want to know about the chaos? As in what kaons are or about their decay and why we've not, like, why we violate CP? Okay, so kaons are just, they're mesons. They're composite particles made of, as I think, uh, K0 has this down and anti-strain, I believe, and K0 bar has strain and anti-bond. Yeah, down and anti-strain and strain and anti-bond. They're just composite particles made of two quarks. The K0 and K0 bar are uh, antiparticles of each other, as they're related by a charge configuration. So the thing is that if you don't exactly understand the thing about kaon decay, it's, if you write it down, right, then how do I explain? Okay, you can basically, you can have you can construct two as someone was talking about superposition and whatnot, right? So these K0 and K0 bar are the two uh, charge mass eigenstates, as in the sense they are the masses that we observe. But there are also CP eigenstates that we can conserve. We can construct with those. So you can make two possibles. The one with an anti-symmetric wave function, which is like your K01 will be half K0 minus K0 bar. Sorry, not half, 1 by root 2, because it needs to we need to normalize the function, right? And then K02 will be 1 by root 2 K0 plus K0 bar. Now, the thing is that both of these have a corresponding CP odd and CP even states, as in how they function. Like if you change like an odd and even would refer to the eigenvalue of the CP transformation. So say go from if you go from a particle to an antiparticle and change the parity, then whether there is an overall negative sign or an overall positive sign that comes to it. Now, because of these constraints and because of the charge and parity eigennumbers of the pions themselves, there are restrictions into what pions a certain eigenstate can decay into and what rates those corresponding decays will have. But that does not match with what we've observed. We've seen decays which should not be allowed. We've seen like you expect that a K short will only decay to 2 pions, but we've also seen a decay to 3 pions, which is not something that should be allowed. So that's why we see that CP is violated. Not sure what you mean by relative time of fixed time. As in, there is no fixed law, and like, there is no universal time if that's what you're asking. Even in quantum mechanics, you're just studying the evolution of that particular system based on the block in that of that particular system. There's no universal. All right, so it is 12:55. Let's start again. Wait for 30 seconds. Everyone's back. All right. So Feynman diagrams. Yeah. Okay. Whatever the slide headings or the free body diagrams for particle physicists, sure. That's such a gross understatement for what Feynman diagrams are and how powerful tools they are. Um, you're essentially every interaction that needs to be written down. You write something called the Lagrangian of the system of an interaction. It has different terms, it has different propagators, different vertex factors, all of this you can see if you zoom into that. Like, yeah, the first thing in the Drake meme over there is what an average interaction looks like. But this isn't even a very complicated interaction. It's just a four, like, it's, that thing on the top is representing the thing on the bottom. That is exactly what it's representing. And it's not even in the full form. So, you know, you have, when you use something called the Feynman rules, you can represent any interaction so simply instead of having to write down a whole Lagrangian with 50 different terms. All of this can very nicely, very simply be represented just in Feynman diagrams. And you can, there are different rules. And so for writing all three interactions, right, which all of these rules have all symmetries built into them. So it becomes a very nice tool. You have your Lion and the symmetries. Like it becomes very intuitive when you know the rules for Feynman diagrams. So not to see what decays and what interaction could be allowed, what would be forbidden, and not only that, like when you actually use the Feynman rules, you can write these Lagrangians, you can write the amplitudes, you can just hypothesize any random decay. You can find what the decay rate would be, and it's brilliant. So just a basic way to understand the Feynman diagrams is there's a space and a time axis. Okay, the space axis is your y-axis, your x-axis is time axis. So anything when you're going from left to right, you're seeing the evolution in time, and you're going up to down, you're just seeing different particles in different points in space. Now, antiparticles are represented with a backward arrow. So if you look at the, I mean, yeah, the thing on top and the thing at bottom, you don't know the label A, B, and AB. Let's say 1AB and 2AB. So the difference between 1A and 2A is that you have, in 1A, you have an incoming electron, you have an incoming photon, and the electron absorbs the photon and just the energy of the electron increases. You have a more energetic electron. When you look at 2A, even though the arrow is going backwards, back in time, that's just how you represent it because it's something called um, you, you you can Google this if you're interested. Just look up Feynman-Stückelberg interpretation of antiparticles, where antiparticles are just imagined to be particles going backwards in time. Again, it's just a neat mathematical trick. It's not what it actually is. Don't go on thinking about antiparticles travel backward in time, etc., etc. It's just how you do the math. Makes the math much easier. That's all. So here you look at like 2A is just a positron. You have an incoming positron and incoming photon. The positron observes the photon and its energy increases. Yeah. Similarly, 1B and 2B, where you have an incoming electron or an incoming positron, it emits a photon and its energy decreases. As simple as that. So you see that as you see along the x direction, time is increases. So here it's absorbing in both the A's, it's absorbing a photon, and in the B's, it's emitting a photon. So you guys understand that? All right. No questions. I'm assuming, hoping you understand. So um, now all of these vertices, every conservation law needs to be applied. Like your energy and momentum need to be conserved, charge needs to be conserved, uh, lepton number, barrier number need to be conserved. If it's a stronger electromagnetic interaction, flavor and strangeness needs to be conserved, and so on and so forth. Right? So using all of these rules based on the particular interaction which you observe, which you not observe, you can draw vertices, you can construct different decays, different processes, and see what would be forbidden, what would be allowed. Now, the, all the fermions are represented by solid lines. Bosons are represented with different types of Wiggly lines, depending on the type of boson it is, like photon or W plus minus or WC boson is denoted with this thing that you see here, right? This waveform as such, like a sinusoidal wave, and a gluon is represented by a spring, because that's 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 the neatest way to understand how the gluon works, right? As the range increases, the force becomes stronger and just pulls it more. The same way, like you pull a spring apart more, it will pull back more. So that's why the gluon has a spring type line in the finding method. Now, coming to virtual particles, okay, I'll get to those in a bit. Here, basically, this is what is called a vortex, right? This is one vortex. All of these are singular vortices. Now, you bring about different vertices, you get what you call as interactions. Now, any okay, so let's let's compare these two. I'm sure you must have heard about Baba's scattering. Even if you don't know what it is, you must have heard the word at some point, right? It's an electron scattering with a positron. You have one electron, it emits a photon, uh, loses some energy, and positron gains some energy. Or it could be the other way around. So the positron emits an electron and emits a photon, and the electron absorbs that photon. So there is some energy transfer between the two through this photon. Now, this photon over here, which is represented by a vertical line, is a virtual photon. It is not something that actually exists. It won't. You can't actually observe this photon. So that's a virtual particle. Any particle that you know, uh, any line which exists vertically will end up being a virtual photon. Any line or a virtual particle, not necessarily just a photon, will be a virtual particle, and any line which exists horizontally will be a real photon. So here, when you look at the second diagram over here, again you have an incoming electron positron and you have an outgoing electron positron. So the end states are the same over here. But there can be two types of interactions between an electron positron, which give you an electron and positron at the end as well. The second one is the very famous annihilation and pair production thing, which I'm sure you must have all heard about in some top science context. Electron positron will annihilate to give like an insanely high amount of energy. That again, the opposite of that is pair production. That same photon can also make an electron and positron. In pair production, you must have heard in the context of Hawking radiation or something, I suppose. So these two different processes, they um, what's the word? Sorry, I'm going to forget a word for the fixed photon. They don't interact. Uh, yes. I will get back to that word when I remember it. So basically, these are two competing processes which, do the amplitudes of these interact. You can have both of these. So both of these are observed. When you have an electron positron and you have it could have happened through either of these pathways, and that's with different rates and different amplitudes. So we won't look at all of these Feynman diagrams because they're much like they can be very complicated, but I'll just briefly go over this. So when you're looking at beta decay, right? Something that you heard about earlier. The first diagram is what you see. You have a neutron, which gives you a proton and an electron and a neutron, right? That's the beta decay equation that you have all heard. You've all seen it. So what's actually happening to the right, you see as in the center, you see what's called a quark flow diagram. So the first, like you look at the neutron, they start at the bottom. The first up and down quarks stay as they are. There is no change at all. Okay? The last down quark decays into an up quark. Through this, it emits a W minus while it decays into the upward because the charge at that vertex needs to be conserved, right? The down quark has the charge is minus 1 by 3 and the upward charge is 2 by 3. So that needs to be conserved at that vertex. And the W minus decays into an electron and an electron antineutron. Cool. Similarly, this would be the right side is what proton decay would be if it were observed, but we haven't observed it. And there are, if a proton were not a stable particle, our universe would not exist as it does. And there are a lot of, through experiments, we have certain limits on proton decay, wherein the lifetime is at least of the order of 10 to the 35 seconds or something. I don't remember the exact number. So yeah, protons are pretty damn stable particles. Now, when you look at again, some neutral interactions governed by the C naught won't change the flavor. There's just a transfer in the energy. It's basically just a heavier cousin of the photon. That's all the C naught is. It does not bring a lot of new interesting physics like the W or new interesting types of interaction that the W bosons do. It's just a heavier cousin of the photon. Um, okay, so there are W self interactions which exist. Like you mentioned that photon self interactions don't exist. With the W plus W minus, that's possible because they themselves are charged, right? Because the photon is not charged, you can't have a photon interacting with another photon because the electromagnetic interaction is through charge, is through electromagnetic charge. Since the W plus and the W minus have a charge themselves, it can interact with, like they can interact with each other, which is I think someone had asked a question about the graviton as well. So I think there was another question about red, green, uh, red, green and blue making anti-red or something. So yeah, basically green and blue. I'm not sure if it was asking if they can annihilate a red quark, but the color is sort of similar. Yes, when you have, at vortices, so far when you look at electromagnetic interactions, we've conserved charge. When you have strong interactions coming into play, you also need to conserve the color. So the gluons, there are 8 gluons depending on their color. Uh, Charges. Like, you have one photon, you have three vector bosons, right? W plus, W minus, and Z, and you have 8 gluons. You have the different color combinations. So these are the all of the different kinds of vertices which can exist, or the allowed vertices for the strong interactions. And that is it on quantum diagrams. All right, yeah, this is something I must have heard. Just give me a minute when your phone running out of charge. Sorry.
Can you guys hear me?
Yeah, yes, you can hear me.
All right. So yeah, to everyone asking, like, I mean, you guys are here, so you're probably not asking that. But when I usually tell people about my interest in physics and particle physics, especially on the theory side, most people ask what's the point, and so like theoretical physics today is like generations ahead of uh, experimental particle physics. But even when you look at experiment, many people would be like, okay, but what's the point? So that okay, CP is violated, like duh. So what? Um, bunch of you know um, things come to mind. There's this. Oh, it's probably just an urban legend, but it's actually pretty cool. So when this guy, what's his name, Maxwell first discovered electromagnetic induction, right? Uh, Apparently, some friend of his who was a member in the House of Lords came over and they were just talking about it, and he was like, "Okay, so you run a magnet through near a compass and through a coil and you see some current. So like what? Like what am I supposed to do with it?" And Maxwell apparently said something along the lines of, "I don't know what you're going to do with it or how exactly anyone's going to do anything with it, but I'm sure that 50 years down the line, your government will be charging a tax based on this." So, yeah, to anyone asking why do physics, what's the use? I'm sure there is some use, but that use is not for the physicists to worry about. That's why, engineers exist. That's why they come up with stuff. Like when you look at general relativity, it's such an obscure mathematical, it was such an obscure thing. It's the the tensor algebra involved in relativity is insanely difficult. It's not something you would expect to be relevant in day-to-day life. But GPS would not work at all if you didn't take relativistic considerations into account. In fact, I think even a lot of developments at CERN in accelerator technologies have led to a medical this thing also like the PET scan, that uses positrons. Like all of that comes from people pushing the boundaries of physics and pushing the boundaries of technology every day. But that being said, that's still not why we do physics. This is my favorite line about physics. It's Feynman said it. It's a little tongue in cheek, and I'm not sure if it's appropriate for this, um, official summer school thing, but whatever. Here goes. He said that physics is like sex. Sure, it has use, but that's not why you do it. You do it for the fun. On that note, we finished our discussions on Feynman diagrams and moving ahead. Now, so far you've seen everything about the standard model, right? And you might think, okay, it explains everything. But it's difficult to just comprehend how successful the standard model actually is. Like when we are looking at, problems with the standard models and experimental problems at least, very few results have deviated from the standard model. One of the most telling, the biggest experimental threat to the standard model right now is something called the uh, magnetic moment of the muon. The like it's You might have heard about it as the G minus two abnormality. Now, this is a like it's very difficult to comprehend how successful the standard model is, because when we're talking about its biggest threat being of the observed value of the magnetic moment of the muon is off from the expected value calculated by the standard model at, I believe, the 13th decimal place. So just imagine, where else in physics are you worried by the fact that the 13th decimal place is not matching with what you calculated it to be? That is how strong the standard model is at predicting everything. But still, there are a lot of other problems with it. So most of these are theoretical. There are very few experimental issues, but most of these problems are theoretical. Now, experimental issues, one I mentioned, the muon magnetic dipole moment, and there's also some decay, like irregular decay rates in the beta meson. Um, Now, all of these are just expected diversions. Now, we aren't sure. So the thing is that in particle physics, right? Whenever we talk about deviation from any particular observed value, we need it to a particular amount of standard deviations. So the the threshold is, I mean, it's just arbitrary, but 5 sigma is what is needed to claim that there is a deviation from the standard model. We haven't found any 5 sigma deviation. Because why it's 5 sigma? Because um, I mean, when we are talking about the precision that we are, right, there could be a lot of errors just purely because of experimental error. Your resolution could be off, and that's why mm, whenever some a particle accelerator runs, we the LHC, we Fermilab, anything, you have like hundreds of thousands of data sets, and it's all a statistical game at that point. So you need a proper, you can't just observe one event and be like, hey, this deviates from the standard model. Because mm, if you find only one event that deviated, you most probably messed up while making that measurement. That's why you need at least a 5 sigma deviation. So whenever I talk about the muon magnetic dipole moment or beta meson decay, these deviations are much lesser than 5 sigma. The actual most pressing problems with the standard model are more theoretical in nature, or you know some unexplained phenomena. Now, the strong CP problem, again, as you saw, that CP is violated in the weak force. Now, mathematically, there is no reason that CP should be conserved for the strong force. So, it would be expected to be violated, but we haven't seen a single violation of CP in any system that has a strong interaction only. So, we expect violation, but we haven't seen it. Now, when we looked at lepton number conservation, I mentioned that all the lepton flavors are conserved individually, except for something called neutrino oscillations. Now, neutrino oscillations lie outside the standard model. They were hypothesized to come up with what is known as the solar neutrino problem, wherein we were seeing way fewer neutrinos coming from the sun than we expected. Like, um, and this is an off-quoted number. I think you look at. Uh, I mean, you'll have something like a billion neutrinos passing through your thumb every second or so. Like that's the number that's thrown around usually. But anyway, so there are a bunch of experiments to measure the number of neutrinos coming from the sun, and most of them are off by a factor of around half, one third. And a bunch of different solutions are proposed, but finally what has been observed now later on as well is that neutrinos can oscillate, as in they can change their flavor. You can start off with an electron neutrino, and at some point, that electron neutrino could change into a muon neutrino or a tau neutrino by itself without any interaction, without any W goes on or anything else being emitted. Just the electron neutrino changing its flavor. Now it so happens that these neutrino oscillations, again I can't get into the math over here, but for neutrino oscillations to be possible, you can't have massless neutrinos. They need to be massive. Otherwise, those oscillations just sort of cancel out. And as soon as you make neutrinos massive, it comes up with a bunch of issues in the standard model, like including neutrino masses in the standard model is sort of possible, but it gets very dirty and causes a bunch of other issues. So neutrino oscillations are something that exist outside the standard model, and it's something that we have definitely observed. So as successful as the standard model is, it does have shortcomings, and there are a lot of things which are not explained by it. Obviously, gravity is not explained by it. We don't know how to quantize gravity. As I mentioned earlier, one of the biggest um, challenges in theoretical physics today. Dark matter and dark energy is also something that we don't have any idea about. I'm not sure if this is being covered in other sessions more on the astronomy side, but from cosmology, we have very, very good reason to believe that dark matter and dark energy exist. Dark matter we know from the galaxy rotation curves that we see, right? That was the first indication of dark matter. It's like you can just you can easily write gravity. You can just balance your gravity and your centrifugal force to find out the speed of the rotation, and based on the speed of the rotation of a lot of galaxies, of most galaxies for that matter, then they need to be much heavier than what they seem to be based on our visual astronomy, based on any stellar matter that we see, or any interaction with the gases with hydrogen between those two. Like hydrogen is very light anyway, so that won't really affect much. So we expect there to be a lot of dark matter. It's called dark because it does not interact electromagnetically. It does not interact with light. So there's a lot of unaccounted mass in the universe. The dark energy is what drives the accelerated expansion of the universe. Like the expansion is accelerating. We don't really know why. It's accounted for by something we call dark energy. These are just terms that you add in when you write Einstein's equation or Hubble's equations. You add another term to account for that acceleration. We don't know where that's coming from either. Now, see, these are all up until here. It's actual problems, right? The next four are aesthetic problems, in the sense that when we expect a theory of everything, when we expect something that explains something so well and which explains almost everything, we want it to be beautiful. We wanted to have some mathematical elegance and simplicity attached with it, and not be cluttered. So there's some things that we can't explain, and it just doesn't sit well with physicists about why we can't explain this. So the Koide formula is basically a relation between the masses of the leptons, as in I think, if I remember correctly, it goes something as me plus m mu plus m tau by root me plus root m mu plus root m tau whole square. That gives almost exactly the value of that is 2 by 3. For masses which are very arbitrary, the actual electron muon tau masses are very arbitrary and have very different scales. But for some reason, this comes down to 2 by 3, which seems a little fishy. We don't really know why. Now, similarly, the CKM matrix. The CKM matrix is it basically talks about the strength of the couplings between the different flavors of quarks. So, you'll have a top quark that decays almost exclusively to a bottom quark, and not to, uh, a down quark or a strange quark. Similarly, a a charm quark will decay more to a strange quark than a down quark. So all of these couplings, these numbers as to how often what decay happens, these are all Uh, like it's a matrix. It's a 3 by 3 matrix with different coupling strengths, and it's sort of like a rotation where you have your flavor eigenstates on one side and your mass eigenstates on another. So it's one matrix rotating, you know, mm, like like normal linear algebra, right? You have a matrix acting on a vector and it rotates it. So on, like that's the usual thing. So we don't know where these numbers come from, where the couplings come from. All of these have just been put in by hand based on observations. And the fact is that there are 19 free parameters in the standard model. All the masses, which are the masses are basically the strength of the Higgs couplings or the CKM matrix and a bunch of other parameters which exist. So when we have a theory that explains everything so well, but we have to put in 19 parameters by hand and not just to any rough, like some of them need to be extremely accurate. There's something called the hierarchy problem. I don't think, yeah, it's not mentioned here. There's something called the hierarchy problem, as in for the Higgs boson to have a stable mass, um, we we need to specify certain couplings with the Higgs to the 18th decimal point. If they're not that accurate, if those couplings are not exactly that to the 18th decimal point, it all goes out the window. So that just doesn't feel very natural, right? So it, it so there's good reason to believe that the standard model is just a low energy approximation, a low energy limit of another theory which exists, which is UV, which holds at higher energies as well. So that's why we look at physics beyond the standard model. And oh yeah, I mentioned the gauge group earlier. Okay, wait, I completely missed matter, antimatter. Sorry. So obviously you guys know what antimatter is. You've heard about it today, and I'm sure earlier as well in some pop culture reference, if not properly. So, and you know that whenever you have matter and antimatter collide, there'll be like a lot of energy, even though photons are emitted. Now, if there were equal amounts of matter and antimatter in the universe, you would see random bursts of energy everywhere, right? So obviously that does not seem to be the case. We don't see, just random bursts of lots of light occurring everywhere around us. So obviously the universe has only matter and no antimatter. But why? Mathematically, both of them have the same footing. They're treated similarly. So why is there more matter and less antimatter? We need to explain that. Especially, so there are we need to generate this asymmetry between matter and antimatter, and that's actually something I am working on right now. Something called baryogenesis, where we we try to find decays and processes where there is baryon number violation and there is CP violation, through which you can cause an increase in the number of baryons, as in number of quarks, and a decrease in the number of antiquarks. So there is an asymmetry. You produce more baryons and less antibaryons, more matter and less antimatter. So we're just trying. It's one of the many different ways in which you could have a matter antimatter asymmetry, which we know exists, even though we don't know why it exists. So we're just trying to explain how it came about. Now coming to the gauge group of the standard model, it's basically this. All of the symmetries of the standard model are represented by this one line that you see over here, SU3C cross SU2L cross U1Y. What does that mean? These are three different groups, and the cross is just the product of the group, the product of those groups. Now, all three of these groups specify some interactions. Now, when you look at U1, U1Y talks about the electromagnetic interaction. So the U1 group has one generator, which is the photon. The SU2 group uh, describes the weak force. SU2 has three generators, which are the W plus, W minus, and Z. Now, all of these generators, why it has these generators, it's just like that's just from normal linear algebra. There's no physics as to why they should have one generator, why they should have three generations. It's just linear algebra. But what we get from linear algebra matches our observation. Similarly, SU3 gives you eight generators, which are the eight gluons which we've seen. So all of this is group theory. There's just math. We don't know why. Um, I mean, we have no reason to believe that, it becomes a rather philosophical question. We're just doing some math and predicting a bunch of actual physical observations that we're making, and writing such complex things just using group theory, which is just purely mathematical. There is no physics to it, and we're predicting things, we're explaining things, and it's insanely beautiful and powerful. No, yeah, just another XKCD. I mean, all of my presentations are like full of XKCD comics. Um, if you don't find it funny, I mean, I feel sad for you. But yeah. Yep. Coming to my last slide. Um, we spoke about every problem that exists with standard model. What solutions do we have? Guts are grand unified theories. We've already unified. I think there was something on unification earlier. Again, because I remember this XKCD comment being there. Um, weak and electromagnetism have been unified into the electroweak. Strong has sort of been unified, but not exactly. And gravity is just out there, completely different. So we need to find one theory that unifies all four forces, because we expect all these four forces to be different manifestations of the same force, because that's what we've seen with the electromagnetic and weak forces. So it solves a lot of problems, especially the hierarchy problem. Now, coming to one of my favorite, okay, loop quantum gravity and string theory are just buzzwords. I'm not going to tell you about them because, to be honest, even I don't know a lot about them. They're just, mm, I mean, insanely beyond the scope of this conversation and me as well. Um, I'm just an undergrad. You don't do this stuff till like you're well into your PhD. So it's cutting edge stuff that needs years of maths to get used to. Supersymmetry is something that everyone thought was the final savior to every problem in particle physics, because it works beautifully. It explains everything, right? It solves most of our problems. But for some reason, it doesn't seem to be true. We've not found any indications of that at all. What it basically says is that for every fermion, there's a corresponding superparticle or like sparticle cousin in as a boson, and every boson has a corresponding fermion. Like there's just it increases by spin half. So you have your spin one electron, sorry, spin half electron, and there would be a spin once electron, which has all the same properties of like the same mass, same everything else, and only this thing the spin increases and it becomes a boson. So all of those particles just have like an S added to it for like particles, and I mean some of them are like gives to a like a, it can be funny sometimes. Like you have the top quark and the stop quark. Come on. Anyway, so for a lot of reasons, supersymmetry solves everything, and it's so sad that we have not seen any indications of it. Like we've probed very high energies at the LHC, but we haven't seen any, even no indication of any particle. Supersymmetry is called SUSY, if you've seen memes or you've heard about it. So we've not seen any indication of SUSY, and that's really sad. Like even the current experimental thing places a lot of constraints on SUSY, that even if it exists, it would not solve most of the problems which we expect to be solved today. So for decades, Suzy was thought to be like, I think they came up with it in like the 80s or something. For decades, it was thought to be, the solution to all of our problems. But it's 2023 now. There's nothing. It's sad. Finally, coming to division algebras, which is something again that I worked on a couple of years ago. Um, it's a very group theoretic approach to all of this. It tries to explain at least the free where the free parameters come from. Um, a division algebra is any like set of numbers on which the operation of division can be defined, right? So when you look at vectors, vectors are not a division algebra. You can't divide one vector with another. So there exist only four normed division algebras in maths. Normed as in they have a norm, a modulus. Like you know what I mean by norm, I assume. Like when you have complex numbers x plus iy, the norm is root of x square plus y square, and that basically. So there exist only four norm division algebras. First one being real numbers, of course. Second one being complex numbers. Third being quaternions, their dimension four numbers, where you have 1, I, J, and K. Where I, J, and K are all square roots of minus 1. And lastly, octonions, which are a dimension 8 extension of similarly. You have E1, E2, E3 up till E7, all of it square to minus 1. Now the first three are found everywhere in physics. You have, real numbers, of course. All your observables are real numbers. Complex numbers are also very important you just look at the Schrodinger equation. You don't even need to go beyond that. You can't write the Schrodinger equation without having an iota in there. So complex numbers are not, imaginary is just a really sad misnomer. They're not, there's nothing imaginary about them. They're as real numbers. So it's unfortunate that many people just think of it as imaginary, but they're very real and they're necessary to explain what goes on in our world. Similarly, quaternions, the dimension four algebra, are needed to write some stuff in relativistic quantum field theories. You write some equations, they can't be written as spinor equations. You need to write them as quaternions. But there has been no widespread use for octonions in physics. So what we were trying to do is that we were trying to rewrite uh, the standard model Lagrangian in terms of in using octonions instead of spinors, which is what are usually used, and recreate and see what happens. And some people have found that charge quantization was found coming in from the algebra. So we don't know why charge is quantized in the way it is, right? And what I was particularly trying to do was find the mass ratios of the quarks from the algebra itself, which so yeah, we made some progress, but it was decent progress, I suppose. So that's what we're trying to find the some of the 19 free parameters, and that is it. That's it for the standard model. As it's the most successful thing to come out of science on the whole with respect to how many things it explains, the precision to which it explains things. It's unreal. It's very difficult to comprehend. Like just imagine 18th decimal place is what we're worrying about at this point. We know everything. We know the first 17 decimal places perfectly. If the 18th one isn't matching and we're like, oh no, it's all falling apart. That's how accurate it is. And not just for one thing, everything that you look around you except for gravity is explained by the standard model. It's immensely powerful, immensely beautiful, very simple mathematical structure, all about symmetries. And I hope you guys enjoyed today. That is it from my side. I'll head over and see what questions there are. How bosons create fermions? I'm just going through all of the why we can't predict precisely. What are the factors that's stopping it to calculate precisely? I'm not sure what this is about, but see, we can calculate everything up to infinite precision theoretically, but at the end of the day, comes out that all the decay rates that you calculate, everything will in some way depend on the strength of those interactions, the masses, the charges. So, and those we can only measure so accurately. So, in the end, your calculation of something else depends on your measurement of something you had measured earlier. And it can only be as precise as your earlier measurement. So, that's one of the main reasons as to why we can't have infinite precision when we're calculating something. Yes, the dark matter would have to interact with the Higgs field because it has mass. It does not interact electromagnetically. We expect it to maybe interact weakly. There are some models which are called WIMPs, weakly interactive massive particles. And again, another testament to the humor of theoretical physicists. WIMP was just an, I think, interesting thing that ended up. So all dark matter candidates have interesting names. WIMPs, I told you, there are also machos, which are massive, compact halo objects. Then there's Rambos also. I don't remember what Rambo stands for, but yeah, like at this point, they're just trying to have fun. Oh yes, my WhatsApp number. Yeah, I don't think I'm on the group. I wasn't actually supposed to take this session, so this was just impromptu yesterday. Vaibhavi was supposed to take the session, and unfortunately, she had some issues. Electricity cut for the last 2 days. Yeah, you can post. I'm an undergrad. I'm from the physics department. I am going into my final year now. I just finished my fourth year, and I'm working on particle physics right now. I'm working on something called baryogenesis, as I mentioned. Yeah, I've put my phone number in the chat. If you guys have any questions, feel free to DM. Hopefully, by the next talk, which is on nuclear physics, I think Vaibhavi should be back. She just had some personal emergency right now, so she couldn't come. Until then, if you guys have any doubts, you can put them here. I'll stay here for about 5 more minutes. I think we can stop the recording. Anushka, I'll be around for about 5 minutes more. If you read something, yeah, stop the recording. If you like, you can, as I said, if you don't want to get into the math, Wikipedia is a pretty good resource as well. If you want to get into the math, Griffith's elementary particle physics, and someone also mentioned Palash Pal, I think. Even that's pretty decent.